Picture a Viking navigator on a fog-shrouded sea, holding a crystal to the grey sky and somehow finding the hidden sun, a feat that modern science says should be impossible, yet might actually be true. So sit back, grab a cup of tea, and get ready to explore how Vikings may have navigated treacherous seas using mysterious crystals. We'll discover why medieval sagas describe magical sunstones that revealed the sun through clouds, examine how modern science discovered these legends might be true, and learn what Viking navigation ingenuity, optical physics in the medieval world, and the remarkable possibility that Norse sailors understood light polarization 1,000 years before modern science, tell us about human innovation in the face of nature's challenges. The North Atlantic is a navigator's nightmare. Even today, with satellite guidance and weather forecasting, these waters challenge experienced sailors. Imagine facing them in an open wooden ship with no compass, no sextant, no charts, just your experience, courage, and perhaps a mysterious crystal that saga writers called the sólarsteinn, the sunstone. For Vikings venturing from Norway to Iceland, from Iceland to Greenland, and even to the shores of North America, navigation wasn't just a skill, it was the difference between discovery and death. The fundamental challenge of Viking navigation seems almost insurmountable by modern standards. Magnetic compasses wouldn't reach Europe until the 12th century, well after the Viking Age's peak. GPS and radio beacons were 1,000 years in the future. Even the astrolabe, that medieval computational marvel, was unknown in Scandinavia during the Viking expansion. Yet somehow Norse sailors routinely made 1,000-mile voyages across open ocean, finding small islands in vast seas with remarkable accuracy. Consider the sheer audacity of sailing from Norway to Iceland, 750 miles of open ocean where missing your target by even a few degrees meant sailing past into the empty Atlantic. Or the voyage from Iceland to Greenland, where favourable conditions for sailing coincided with the foggiest season. These weren't desperate refugees fleeing in any direction. They were calculated voyages that found specific destinations. How did they do it? The sagas, those remarkable windows into medieval Norse culture, offer tantalizing clues. In the Saga of King Olaf, dating from the 13th century, we find this intriguing passage. The weather was thick and snowy. The king summoned Sigurd and asked him if he could tell where the sun was. Sigurd took a sunstone, looked at the sky, and saw from where the light came, from which he guessed the position of the sun. Here, in a text written within living memory of the Viking Age, we have our first hint of the mysterious sunstone. The reference appears almost casually, as if readers would understand what a sunstone was and how it worked. This suggests the device was common enough not to require explanation. Another saga, Hrafns Saga Sveinbjarnarsonar, mentions a sólarsteinn in a similarly matter-of-fact way, describing how the stone could reveal the sun's position even in overcast conditions. These aren't mythological tales of Thor's hammer or Odin's ravens. They're presented as practical navigation tools. Yet for centuries, scholars dismissed these references as fantasy or metaphor. How could any stone reveal the sun through clouds? It seemed as impossible as the other wonders described in sagas: berserker strength, prophetic dreams, or swords that never dulled. The sunstone joined the catalogue of Viking mythology, interesting but not factual, until science caught up with saga. The breakthrough came from an unexpected direction: the study of light polarization. To understand how a sunstone might work, we need to grasp a peculiar property of sunlight that human eyes can't normally detect. When sunlight enters Earth's atmosphere, it doesn't just illuminate, it scatters. As light bounces off air molecules, it becomes polarized, meaning its waves align in particular patterns. These patterns are consistent and predictable, radiating outward from the sun's position like invisible spokes on a wheel. Under clear skies, this polarization is strongest at 90 degrees from the sun. Even when clouds obscure the sun itself, the polarization patterns persist in the light that filters through. It's as if the sun leaves a signature in the sky that remains readable even when the sun itself hides. The human eye can't see this signature, but certain crystals can. Enter Iceland spar, a form of transparent calcite found abundantly in Iceland. This crystal has an unusual property called birefringence, or double refraction. When you look through Iceland spar, you see double. The crystal splits light into two separate beams. More remarkably, these two beams respond differently to polarized light. By rotating the crystal while looking through it at the sky, an observer can detect changes in brightness between the two images that reveal polarization patterns. The technique seems almost magical, but the physics are solid. When you hold Iceland spar up to a cloudy sky and rotate it slowly, the two images you see through it will alternately brighten and dim. The point where they match in brightness indicates the direction of polarization, which in turn reveals the sun's position. Modern experiments show this method can locate the sun within 1 to 2 degrees, accurate enough for navigation. But could Vikings have discovered this sophisticated optical phenomenon through trial and error? Consider their circumstances. Iceland, where many Viking expeditions originated, happens to be one of the world's best sources of optical quality calcite. The crystal was familiar to Norse people. It appears in burial goods and household contexts. Someone handling these crystals would inevitably notice their strange double vision property. From there, it's a small step to discovering that the doubling changes with orientation and lighting conditions. Vikings were intensely practical people who survived through careful observation of natural phenomena. They read wave patterns to detect invisible land beyond the horizon. They followed bird migration routes to find new territories. They used the color of clouds to detect ice or land beneath them. Discovering that a common local crystal could reveal the sun's position fits perfectly with their pattern of exploiting natural phenomena for navigation. Archaeological evidence supports the sunstone hypothesis, though indirectly. While no crystal has been definitively identified as a navigation tool from a Viking Age context, we do have suggestive finds. In 2013, a crystal was discovered aboard an Elizabethan shipwreck near the Channel Islands. The ship sank in 1592, well after the Viking Age, but the crystal, a piece of Iceland spar, was found near navigation instruments, suggesting it served as a backup when magnetic compasses failed near cannon or iron fittings. More intriguingly, archaeologists have found calcite crystals in Viking Age contexts that show no obvious decorative or practical purpose. A crystal discovered at a Viking settlement in Greenland seems particularly significant. Why transport a fragile crystal across dangerous seas unless it served an important function? While we can't prove these specific crystals were navigation tools, their presence in exploration contexts is suggestive. The lack of crystals in Viking ship burials might seem problematic, but consider this. Valuable navigation tools would be jealously guarded by living navigators, not buried with the dead. The knowledge of how to use a sunstone might have been restricted to master navigators, a trade secret passed from teacher to student, rather than recorded in writing. This would explain both the casual saga references, everyone knew they existed, and the lack of detailed instructions, few knew exactly how they worked. Modern experimental archaeology has put the sunstone hypothesis to rigorous testing. In 1967, Danish archaeologist Thorkild Ramsku first proposed that the saga references might describe real navigation tools. His ideas were initially met with skepticism, but subsequent research has steadily built the case. Researchers have taken calcite crystals to sea, testing them under various weather conditions. The results are remarkable. Even under heavy cloud cover, the crystals can reveal the sun's position accurately enough for navigation. The Royal Navy conducted tests in the 1960s and 1970s, motivated partly by the need for backup navigation methods in case of electronic failure. Naval personnel with no previous experience could learn to use crystal navigation within hours. Under Arctic conditions, similar to what Vikings faced, the method proved especially valuable, as the low sun angles that make conventional navigation difficult actually enhance polarization effects. A Hungarian research team led by Gábor Horváth has conducted the most comprehensive studies, using computer modelling to analyse millions of possible Viking voyages under various weather conditions. Their conclusion: crystal navigation would have significantly improved the chances of successful voyages, especially on the cloudy routes between Iceland and Greenland. The sunstone wouldn't replace other navigation methods, but would complement them perfectly. The question arises, If sunstones were so effective, why didn't the technology spread more widely or persist into later periods? Several factors likely contributed to their disappearance. First, the magnetic compass arrived in northern Europe by the 12th century, offering a simpler alternative that worked in all conditions. Second, the specific knowledge of how to use crystals for navigation might have been closely guarded by Norse navigators, preventing widespread adoption. Finally, as Viking expansion ended and regular ocean voyages became less common, the specialized knowledge simply wasn't maintained. To fully appreciate the sunstone's potential, we must understand the broader context of Viking navigation methods. Norse sailors used an integrated system of techniques, each suited to different conditions. In clear weather, they used a bearing dial or sun compass, a wooden disc with a central gnomon that cast shadows to indicate direction. Multiple examples have been found, including a fragment from Greenland that shows sophisticated understanding of solar geometry. Vikings also practiced latitude sailing, maintaining a constant north-south position while travelling east or west. They could determine latitude by measuring the sun's height at noon or the North Star's elevation at night. Saga accounts describe checking latitude by comparing the sun's position to remembered landmarks. Sail south until the sun at noon is as high as it was at home on the summer solstice. This method required no instruments, just careful observation and good memory. But what happened when clouds obscured these celestial references? This is where the sunstone would prove invaluable. Viking voyages often encountered fog banks that could last for days, particularly in the Denmark Strait between Iceland and Greenland. Magnetic anomalies in these northern waters would have made compasses unreliable, even if Vikings had possessed them. The ability to find the sun through clouds would have been literally life-saving. The physics behind crystal navigation are fascinating and counterintuitive. Light polarization occurs when photons, particles of light, oscillate in aligned patterns rather than randomly. When sunlight hits atmospheric molecules, the scattering process naturally aligns these oscillations perpendicular to the light's travel direction. This creates patterns in the sky that remain stable even when clouds intervene. Calcite crystals can detect these patterns because of their molecular structure. The crystal lattice splits incoming light into two rays that travel at different speeds through the material, the ordinary ray and the extraordinary ray. These rays respond differently to polarized light. When you rotate the crystal, the relative brightness of the two images changes in a predictable way. The point where both images appear equally bright indicates the direction perpendicular to the light's polarization, and thus reveals the sun's location. The phenomenon becomes visible through what's called Heidinger's brush, a subtle visual effect that some people can actually see without crystals. It appears as a faint yellowish bow tie shape in the sky, perpendicular to the sun's direction. Most people need training to perceive it, and it's easiest to see against a uniformly lit background like a cloudy sky. Vikings might have used crystals to enhance this natural but weak visual cue. Other crystals besides Iceland spar might have served as sunstones. Cordierite, known as Viking compass to mineral collectors, shows strong pleochroism. It changes colour when rotated, relative to polarized light. Tourmaline has similar properties. Some researchers suggest Vikings might have used different crystals for different conditions, selecting tools based on specific navigation challenges. The cultural context of Viking expansion helps explain why such sophisticated navigation tools would develop. The Norse diaspora of the 8th to 11th centuries ranks among history's great migrations. Population pressure, political upheaval, and the lure of new lands drove thousands to risk everything on ocean voyages. The difference between successful colonization and disappearance at sea often came down to navigation skill. Iceland's settlement provides a case study. The first intentional settlers arrived around 874 CE, but they were following reports from sailors blown off course who had sighted the island. Within 60 years, Iceland's habitable areas were fully claimed. This rapid, successful colonization required reliable navigation. Sailors had to find Iceland repeatedly, bringing supplies and new settlers. Random voyagers hoping to stumble upon land couldn't have sustained such organized settlement. The Greenland colonies present an even starker example. Eric the Red's expedition around 985 CE found the only two areas of Greenland suitable for Norse farming, both on the island's southwest coast, hidden behind Cape Farewell's forbidding cliffs. Missing these narrow fjords meant either death in the Arctic wastes or a long voyage home in failure. Yet Norse sailors found these hidden refuges repeatedly for over 4 centuries, maintaining regular contact between Greenland and Iceland despite some of Earth's most challenging ocean conditions. The evidence for pre-Columbian Norse presence in North America, confirmed by archaeology at Lanso Meadows in Newfoundland, raises navigation challenges to yet another level. The sagas describe voyages from Greenland to Vinland that found specific landmarks and returned to the same locations. These weren't random wanderings, but targeted expeditions that required sophisticated navigation skills. Could they have achieved such feats without tools like the sunstone? Skeptics raise valid concerns about the sunstone hypothesis. No saga provides detailed instructions for using crystals as navigation tools. No archaeological find has yielded a crystal with runic instructions saying, "Point this end toward cloudy sky." The crystals found in Viking contexts might have served entirely different purposes: decorative, trade goods, or ritual objects. The argument relies heavily on inference and circumstantial evidence. Furthermore, successful navigation doesn't require technological solutions. Polynesian navigators crossed vast Pacific distances using no instruments at all, relying on wave patterns, star positions, and bird behavior. Vikings might have achieved their navigation feats through similar environmental awareness rather than crystal optics. The human tendency to seek technological explanations for past achievements might blind us to simpler solutions. Yet the convergence of evidence remains compelling. We have saga references to sunstones in navigation contexts. We have crystals with the right optical properties readily available in Viking lands. We have experimental confirmation that the technique works. We have crystals found in maritime archaeological contexts. While no single piece of evidence proves the case, together they build a strong argument. The debate also illuminates how we study the past. For generations, scholars dismissed saga accounts that didn't fit modern expectations. The lesson of the sunstone, that fantastic-sounding claims might describe real phenomena, has encouraged more careful consideration of traditional knowledge. Indigenous peoples worldwide preserve accurate information about natural phenomena in oral traditions. Why shouldn't Viking sagas do the same? The search for Viking sunstones has practical modern applications. Understanding polarized light navigation has improved autonomous vehicle guidance systems. Studying how humans might navigate without electronics helps develop backup systems for GPS failure. The military remains interested in non-electronic navigation methods that can't be jammed or detected. Viking crystal navigation, if real, represents sustainable, resilient technology that modern society might learn from. Science education also benefits from the sunstone story. The mystery engages students who might otherwise find optics boring. Building a working sunstone from hardware store calcite costs a few dollars, but demonstrates sophisticated physics. The interdisciplinary nature, combining archaeology, physics, history, and navigation, shows how different fields illuminate each other. Vikings with crystals make polarization memorable. Museums and tourist sites have embraced sunstone demonstrations. At Iceland's National Museum, visitors can try finding the sun through calcite crystals. Viking festivals feature navigation workshops, where participants learn celestial navigation techniques. These hands-on experiences make abstract concepts tangible and connect modern people to ancestral skills. The sunstone serves as a bridge between past and present. The literary impact of sunstone research deserves mention. Science fiction authors have imagined sophisticated Viking navigation leading to alternate histories. Fantasy writers blend the historical sunstone with magical elements. Even serious historical fiction now incorporates crystal navigation as an authentic detail. The sunstone has entered popular culture as a symbol of hidden Viking sophistication. Climate science offers another perspective on Viking navigation challenges. The medieval warm period, roughly 950 to 1250 CE, coincided with Viking expansion. Warmer temperatures meant less sea ice, but potentially more fog from increased evaporation. Tree ring data and ice cores suggest variable weather patterns that would have made navigation unpredictable. Any tool that improved reliability would have been precious. The economic implications of reliable navigation were enormous. Viking Age trade networks stretched from Greenland to Constantinople, from Dublin to Kiev. Merchants needed to calculate travel times, plan for seasonal conditions, and arrive at markets predictably. Navigation uncertainty meant higher risk premiums, more expensive goods, and reduced trade volume. A tool that improved navigation reliability would have paid for itself many times over. Social stratification might explain the limited sunstone references in sagas. Master navigators held positions of enormous responsibility and prestige. Their specialized knowledge, including perhaps sunstone use, would have been carefully guarded. Saga writers, typically educated churchmen writing centuries after the Viking Age, might have known about sunstones without understanding their operation. They included references for authenticity without providing technical details they didn't possess. Comparative mythology offers intriguing parallels. Many cultures describe magical stones or crystals that reveal hidden truths. Celtic tradition includes stones that show the righteous path. Hindu texts describe gems that illuminate darkness. Chinese mythology features pearls that glow with inner light. While most such references are purely fantastical, the Viking sunstone might represent a rare case where myth and reality converged. The gender dynamics of Viking navigation remain largely unexplored. Sagas occasionally mention women with navigation knowledge, usually in magical contexts. Did some women learn crystal navigation? Were there female navigators whose stories weren't preserved? The domestic context of some crystal finds might suggest women's involvement in navigation preparation, even if they didn't sail themselves. These questions remind us how much we don't know about Viking society. Religious transitions might have affected sunstone knowledge. As Scandinavia converted to Christianity between 1000 and 1200 CE, traditional knowledge associated with pagan practices faced suppression. If sunstone use had ritual elements, prayers to Thor for clear sight or Odin for wisdom, Christian authorities might have discouraged it. The Church brought Latin learning and Mediterranean navigation techniques that displaced indigenous knowledge. Material culture studies reveal the sophisticated Viking understanding of optics beyond possible navigation uses. They produced high-quality glass beads, requiring precise temperature control. They crafted rock crystal magnifying lenses. They understood how to focus sunlight to start fires. This broader context of optical experimentation makes crystal navigation seem less anomalous and more part of a general engagement with light phenomena. The etymology of navigation terms provides linguistic clues. Old Norse had specific words for different types of fog, ice conditions, and sea states, vocabulary that suggests careful observation of navigation conditions. The word sólarsteinn itself is compound. Sol, sun, plus stein, stone, a straightforward descriptive term rather than a mythological name. This practical nomenclature supports the interpretation as a real navigation tool. Modern climate change adds urgency to understanding past navigation. As Arctic ice melts and new sea routes open, lessons from Viking navigation become relevant again. How did Norse sailors navigate in polar conditions where magnetic compasses fail and GPS signals weaken? Their combination of environmental observation and possibly crystal optics might inform future Arctic navigation strategies. Educational initiatives have emerged around sunstone navigation. Science museums offer workshops combining history and physics. Universities use the controversy to teach critical thinking and evidence evaluation. Elementary schools introduce polarization through Viking stories. The sunstone serves as an entry point for complex STEM concepts, making abstract physics tangible through historical narrative. Tourist economies in Nordic countries benefit from sunstone interest. Iceland markets, Viking navigation experiences where tourists sail replica ships and learn traditional techniques. Crystal shops sell authentic Viking sunstones, though without navigation guarantees. Hotels near saga sites offer navigation-themed packages. This commercialization, while sometimes exaggerated, keeps traditional knowledge in public consciousness. The philosophical implications of the sunstone debate touch on fundamental questions about human ingenuity. Did Vikings independently discover optical physics principles that European science wouldn't formalize until the 17th century? Or did they stumble upon a useful phenomenon without understanding why it worked? Either possibility challenges our assumptions about technological progress and indigenous knowledge. Conservation efforts now protect potential sunstone sources. Iceland restricts export of optical quality calcite to preserve scientific and cultural resources. Museums carefully curate Viking Age crystals that might have navigation significance. This preservation ensures future researchers can apply new analytical techniques as they develop. Each crystal might hold clues invisible to current technology. Digital Humanities projects have catalogued all saga references to navigation, creating searchable databases that reveal patterns human readers might miss. Text analysis shows that sunstone mentions cluster in sagas about far ocean voyages rather than coastal sailing. Geographic information systems map possible Viking routes against weather patterns and crystal find locations. These tools bring new precision to old questions. Experimental archaeology continues advancing our understanding. Researchers have sailed replica Viking ships across the North Atlantic, using only traditional navigation methods. While ethics prevent deliberately sailing into dangerous conditions to test sunstones, controlled experiments in challenging weather have demonstrated the crystal's value. Each voyage adds data about what was possible with Viking technology. The interdisciplinary nature of sunstone research exemplifies modern scholarly collaboration. Physicists calculate optical properties, archaeologists excavate crystal finds, historians analyze textual evidence, and sailors test practical applications. This convergence of expertise has transformed a dismissed saga reference into a serious scientific hypothesis. The sunstone shows how different ways of knowing can illuminate truth together. As we conclude our exploration of Viking sunstones, what have we learned? First, that medieval sagas deserve more credit as historical sources. Their mixture of myth and reality requires careful analysis, but dismissing them entirely means missing valuable information. The sunstone reminds us to approach traditional knowledge with both skepticism and respect. Second, we've seen how environmental constraints drive innovation. Faced with some of Earth's most challenging navigation conditions, Vikings potentially developed a solution that wouldn't be scientifically understood for centuries. Necessity mothered invention in the fog-shrouded North Atlantic. Human ingenuity finds ways to survive and thrive against natural obstacles. Third, the debate illustrates how science progresses through interdisciplinary cooperation. Physicists alone couldn't have recognized the navigation potential of optical phenomena. Historians alone couldn't have explained the saga references. Only by combining expertise from multiple fields did the sunstone hypothesis emerge and gain credibility. Modern challenges require similar collaborative approaches. Fourth, we've learned humility about technological assumptions. Vikings achieved remarkable navigation feats with or without crystal tools. If they used sunstones, they understood practical optics centuries before formal science. If they didn't, they possessed environmental knowledge and sailing skills we can barely imagine. Either way, they challenge our chronological chauvinism about primitive versus advanced societies. The sunstone story continues evolving. New archaeological finds might provide definitive proof or disproof. Advanced analytical techniques might reveal microscopic evidence of navigation use on existing crystals. Climate modelling might better reconstruct Viking Age weather patterns. Each discovery adds pieces to this 1,000-year-old puzzle. Whether Vikings actually used crystal navigation tools or achieved their remarkable voyages through other means, the sunstone captures something essential about human exploration. Faced with vast, dangerous oceans, our ancestors refused to remain landlocked. They pushed boundaries, developed technologies, and passed knowledge through generations. The same drive that might have led Vikings to peer through crystals at cloudy skies propels modern humans to Mars. In practical terms, the sunstone hypothesis has already succeeded by inspiring new research, education, and appreciation for traditional knowledge. Museums display calcite crystals differently knowing their potential navigation role. Students learn physics through Viking stories. Tourists experience history hands-on through navigation workshops. The sunstone has emerged from saga shadows into scientific light. As you finish your tea and contemplate this tale of Vikings and crystals, consider what other dismissed myths might hold scientific truth. What traditional knowledge have we overlooked because it sounds impossible? What innovations did our ancestors develop that we've forgotten? The sunstone reminds us that the past holds surprises for those willing to look carefully, even through a cloudy crystal on a foggy day. The next time fog obscures your way, remember those Viking navigators holding crystals to grey skies, seeking the hidden sun. Whether their sunstones were real navigation tools or saga imagination, they represent humanity's eternal quest to find direction when the way seems lost. In that search for light through darkness, for clarity through obscurity, Vikings with crystals speak across centuries to our own navigational challenges, both literal and metaphorical, in an uncertain world.